Yeah. Should I start?
Okay, so we are going to start. So welcome everybody for this last day of conference. And the first speaker of the day is Sujatha Ramdorai from University of British Columbia. And as you can see, the title of her talk is Iwasawa theory over anticyclotomic expansion.
Yeah, thank you. Thanks to the organizers for inviting me to give this talk. There's a problem. I can't see my screen, so I hope you can see. I can see what I'm writing, but I cannot see it on my computer screen.
Okay, we can see it, yes.
Okay. All right. Now I can see it. All right. Okay. So this talk, I want to give an overview of, it's a kind of compare and contrast about the results on Iwasawa theory for the cyclotomic and the anticyclotomic extension. So let's start with K over Q. This is the setting. K over Q is an imaginary quadratic field. And E over Q is an elliptic curve. P is a prime. I'll assume at times I'll have to assume it's greater than or equal to 5. So let me make that assumption. Some of the results are still valid for P equals 3, but let me go ahead and assume that this is the case. And then of course, I've always worked in the cyclotomic extension, but recently for the last few years, well, not even few years, I would say few months, I've been trying to understand anticyclotomic. Earlier, I had just looked at it on and off, and I discovered that it's much more subtle, and there are still a lot of questions which are open in anticyclotomic, which are of interest to me. So I'm just going to talk about that and compare along the way what is known in the cyclotomic and what is known in the anticyclotomic and the problems and the results. So of course, K over Q, this is a degree 2 extension. So Leopold's conjecture tells us that there are two linearly independent imaginary quadratics. So there are two linearly independent ZP extensions. So one is the cyclotomic and the other is the anticyclotomic. I'm going to write KAC. This is cyclotomic ZP extension. Of K. And we are going to be interested in the Iwasawa invariant. We are going to be interested in two objects. So I'll always, irrespective, so I'll use, I'll write, sometimes I might write KC for, oh, sorry, this is the anticyclotomic. And this is, when I just write C, it's going to be the cyclotomic ZP extension. Now, whatever I say is also going to be true for modular forms. But my philosophy has always been try to understand what happens for elliptic curves. And as soon as this is posted on archives, people will do it for modular forms using more or less the same methods. So I'm going to stick to elliptic curves. And, you know, the inspiration for this really comes from one of Mazur's comments. Of course, this is recorded in the paper of Emerton, Pollack, and Weston. And I spoke to Mazur about it a few years back, and Mazur also strongly believes that there should be a mod P Iwasawa theory, which explains congruences. So the type of questions we have in mind is how much of Iwasawa theoretic information on Iwasawa modules associated to elliptic curves arising from elliptic curves and typically we have, you know, we'll always work with the dual Selmer group. And what's the dual fine Selmer group? You must have already heard about the dual fine Selmer group in other lectures. So these are the two groups we are interested in over the cyclotomic extension or the anticyclotomic extension. Is preserved mod P is carried over for the mod P representation. So what do we mean by this? So we have an elliptic curve E over Q. And in this, for today's context, I'm just going to work in this setting, though of course this question can be asked for any elliptic curve and F an arbitrary number field and so on. And then now suppose we have, and we know we are the, we have the Selmer group. So again, if I take, so let me stick to K, the quadratic imaginary extension, and then I'll write F, where F can be either the cyclotomic or the anticyclotomic extension. Then we have the Selmer group over F, and I'll denote by Fn. These are the finite layers. So this is a ZP extension. And so you have the finite layers. So this is a Z mod P to the N, the finite layers. So we define the Selmer group. This is the classical Selmer group. Remember, the Selmer group is always defined with respect to some local conditions. So we'll treat the Selmer group. Let's first do it over finite layers. Selmer group EPN over the finite layer Fn. This will be a subgroup of H1 Ks over Fn. I'll explain what Ks is. EPN, this can be M here, this can be an M. EPN. And then there are these local terms. V in S, and I'm going to write JV of E over VFMs. Okay. So what is Ks? S is going to be a finite set of primes containing the primes above P and the bad primes. So bad primes typically will mean you take the conductor of E and then include those in the finite set. And Ks is a maximal, as always, maximal unramified outside S extension. So these JVs, usually people define these in terms of Selmer structures. It's a more general definition. And what you do is you divide, first of all, you look at the primes V in S. And then there are two kinds, those which lie above P and those which do not lie above P. Then look at the local H1 completions. Take E here. And then you go modulo the image of the Kumar map. This is for the classical Selmer group. And for the others, you just retain. So you're killing some part. So, and you can vary what you want to kill. And then you get different kinds of Selmer groups. But for the classical Selmer group, you kill the image of the Kumar map. So what's killed is the image of the Kumar map. And then, of course, you can pass to the limit over this. Hey, does anybody have an idea of how I make this go away? This okay, it's not going away. So, and so you can define the Selmer group. What did I do? You can take the direct limit, so you get the
Ma'am, can
P.
you click that arrow mark? Maybe.
Which arrow mark here?
No, on the top. You want to get rid of that bar, right?
Right.
Yeah, on the top. Yeah, there is an arrow mark. Can you just click that one?
Oops.
Uh,
Went somewhere.
Not 1 minute. Okay. Can you try to drag it to the extreme right corner or left? Oh, okay.
All right. If it doesn't bother you, it doesn't bother me.
Okay.
Just let me know if you would want me to scroll up and down and I can do it. So you have this extension, then you go up to all the way up to the anticyclotomic or the cyclotomic extension. Then you have an corresponding sequence
Excuse me?
H1KS over. Yeah.
It's a very naive question, but in the local cohomology group, is it E or EPN on the PN torsion?
No, in fact, it will be E, the PN will come outside because I'm defining the Selmer group. Right?
Right, okay.
Yeah. And in fact, I'll put the PN inside, then I'll define what's called the fine Selmer group. H1FS F over EPN, and then V in S, JV of E over F. So let me call this lambda, this map lambda, and put a dot here because I'm going to consider the lambda cyclotomic and also the lambda anticyclotomic. And then you have the fine Selmer group. Let me call that fine Selmer F cell. Again, you define it over the local finite layers, Fn. So here it should be P infinity. H1 Ks over F, EP infinity. The middle one is the same. And then I have, this time I'm going to do this over FV. I complete it at the primes above V, and then I put EP infinity inside. I take it inside. Again, I do it at the finite layers. Sorry. Let me directly take the, where is the, so let me write an F here. I don't know how to erase. So do it at the finite layers, then take limits. So then you get an exact sequence like this. So then, of course, the fine Selmer group is going to be a sub of this. And I treat these as Iwasawa modules. So all of these are modules, Selmer, EP infinity over F. And the fine Selmer F cell, EP infinity over F, are finitely generated discrete modules over, and I'm going to write lambda gamma, but of course gamma is isomorphic to ZP. But this gamma is ZP both for the cyclotomic and the anticyclotomic. So sometimes if I want to say which gamma I'm treating, so then I might write gamma anticyclotomic or the gamma cyclotomic, but the context will be clear. Okay, so again, let me draw this diagram. So I have F over K over Q, and F is either K anticyclotomic or K cyclotomic, and this is ZP, the ZP extension. So these are finitely generated modules, and now what is known? We know that now I'm going to make two assumptions. Well, two different cases. P is ordinary. P is an ordinary prime. And the other hypothesis or the other case is P is supersingular. Now, in these two cases are the classical ones that we study. Of course, E has good ordinary reduction at the primes above P, but these are the two cases to distinguish. Either it's ordinary or it is supersingular. And now already here there's a divergence. Even in the classical cyclotomic setting, there's a divergence. So I'm going to take the dual because I want to work with compact modules. So I'll write co-finitely generated when I'm working with discrete, but the compact modules will be the ones that are finitely generated. So I'll put X cyclotomic E over F. This is the dual. Home, Selmer group, homomorphisms of the Selmer group of EP infinity over K cyclotomic. So F can be, remember, it can either be K cyclotomic or anticyclotomic, QP mod ZP. And similarly, I'll write Y cyclotomic E over K anticyclotomic. This is going to be the dual of the discrete Selmer group, P infinity. Now, this is a divisible Selmer group in the sense I'm working with the divisible coefficients, EP infinity, QP mod ZP. So now in the cyclotomic setting, it's a conjecture of Mazur, and it is known, it was proved by Kato in this case. We know that X cyclotomic E over K cyclotomic is in fact, or I'll just for shorthand, I'll just call this X cyclotomic EP infinity. This is finitely generated torsion. Module over lambda gamma cyclotomic extension. We know this. And in fact, what is also known, this torsionness is also very easily deducible by just analyzing the definition of the Selmer group. And this is due to Hashimori and Matsuno, but in fact, Greenberg, various others known already before, and this is generalizable to a large extent to other bigger extensions as well. So we know that this is finitely generated torsion lambda gamma module. This is equivalent to this sequence here. Remember this, we had this defining sequence. So Selmer of EP infinity over K cyclotomic. I had the H1 Fs over K cyclotomic, EP infinity, and then let me call this lambda cyclotomic now. We had the local terms, V in S, JV, E over K cyclotomic. So this is equivalent to this being a short exact sequence. So you can read this off. This being in torsion, you can read it off by just looking at this exact sequence. Now, this was first proved in full generality by Hashimori Matsuno, and this has very interesting applications. And the way you do it is you analyze the Pothu-Tate sequence, and then you use the Iwasawa theory, what you know about the Iwasawa theory, because this is an ordinary case, and then you use that information to get this. Now, now this becomes interesting, and then we also know under Leopold's conjecture, weak Leopold. Which is a statement that H2 Fs over Ks over K cyclotomic, EP infinity is 0. This is weak Leopold conjecture. So under weak Leopold conjecture, also know that the dual fine Selmer group, Y cyclotomic of E over K cyclotomic is finitely generated and torsion. This is in the ordinary case. And in the supersingular case, we still have weak Leopold. So still the fine Selmer group, Y cyclotomic of E over K cyclotomic and Y anticyclotomic. For shorthand, I just write Y anticyclotomic. This is the dual fine Selmer groups. This is of course over the anticyclotomic extension. And both of these are again lambda gamma modules. And you know that these are torsion even here, or finitely generated torsion. But you know that the cyclotomic, X cyclotomic, that's a dual Selmer group itself, is not torsion in both these cases, and also X anticyclotomic. Nevertheless, in this case, you can read off, however, in the ordinary case, remember you had this if and only if condition. Namely, this was finitely generated torsion if and only if this sequence was short exact. But here you have it is not torsion, yet the sequence is short exact here. So the first thing you would like to understand is whether, how can I read off? Can I read off the torsion phenomena by just analyzing that exact sequence? And then it gets considerably delicate to do this in the anticyclotomic setting. So that's the first remark. And then now we are going to invoke the structure theorem for finitely generated modules. So let M be a finitely generated compact lambda G module. Lambda, I'll just say lambda module. So lambda is lambda over gamma, which is ZP. In fact, you can identify it with the power series in one variable. So this is a finitely generated compact lambda module. Then M is pseudo isomorphic. This just means that the kernel and co-kernel, there's a lambda homomorphism, and the kernel and co-kernel are finite. So up to finite modules, M just looks like there's a free part, lambda to the power R, this is the rank. And then there's a part which is killed by powers of P, some J equals 1 to K, say, J equals 1 to M, say, lambda gamma modulo P to the power J. And then there is a ZP part. There's a P torsion free part. So this is K equals 1 to T, say, of ZP double brackets T modulo some polynomial. In fact, this will be a distinguished polynomial, Fk, to the power some Nk, some integers. So once you have this, you have these invariants. So R is called the rank of M. Rank of M. J is called the summation of all the J's. J equals 1 to M. This summation is called the mu invariant of M. And the lambda invariant is summation of the degree of each of these FKs are distinguished polynomials. So they have a degree. So I take the degree of Fk times Mk. This is the lambda invariant. So now these are the important, interesting Iwasawa theoretic invariants. And in the supersingular case, what happens? We know that the Selmer group, dual Selmer, is not torsion. However, Kobayashi, there are various people, Kobayashi, Kurihara, Pereiro, they introduced what are called signed Selmer groups, which I just denote by Selmer plus minus of EP infinity over F, where again F is either the cyclotomic or the anticyclotomic extension. And again, there is a defining sequence, just like before. So there's a cell plus minus EP infinity sitting inside the first Galois cohomology group, H1 KS over F EP infinity. And this time the local terms, you're going to kill something else in the denominator. You're going to kill, they introduce something like the plus minus parts of the points of the model way group. And then you take the images of those under the Kumar map and then call those JV plus minus. I'll not give you the definition. It's a bit technical, but there is a defining sequence here as well. And then exactly as in the ordinary phenomena, you know that cell plus minus EP infinity over K cyclotomic as well as over the anticyclotomic. Various people have studied these. I'm just mentioning a few names. These anticyclotomic are cotorsion. So in other words, because you have these bunch of cotorsion modules, and then of course you have the usual Selmer, which we know is not cotorsion, but I can study its torsion part. This is not cotorsion, but we will be interested in its torsion part. Torsion part, you can still define the mu invariant. So Maser, at one point, and this is mentioned in the paper of Emerton, Pollack, and Weston, so Maser raises a question whether there is a mod P Iwasawa theory. And Greenberg and Wurzel sort of gave more precise meaning to some parts of it in the following sense. So Greenberg, Wurzel, and then again, there are a bunch of names in the super singular case. So B.D. Kim and various others, but these were the original papers. This is in the super singular case. You can ask the following question. Suppose I have E1 and E2, two elliptic curves as before, such that their P torsion points are isomorphic as Galois modules. Then can I recover the lambda? So then I have the Selmer groups. I have Selmer groups of E1 P infinity over F. And similarly, the Selmer group of E2 P infinity over F. So in other words, I have all these groups. Now I'll just take their duals and the notation should be clear. So I have X cyclotomic of E1, X anticyclotomic of E1. These are the dual P infinity Selmer groups over the cyclotomic extension and the anticyclotomic extension. Then I have the dual fine Selmer groups, Y cyclotomic E1, Y anticyclotomic E1. And then we also have the plus minus. Let me write EI because we have this for both E1 and E2. X anticyclotomic here and then Y anticyclotomic. Yes, the fine Selmer groups are still the same over the anticyclotomic. So here it should be there's no you can define a signed Selmer group, but let me not get into that. So then the question is, when you have this, how do their mu invariants and lambda invariants compare? And Greenberg and Wurzel they sort of initiated this program and we proved some very beautiful results. So they said hypothesis as above in the ordinary case. So we are talking about the ordinary case. That is, I have E1 and E2 elliptic curves over Q such that the residual representations are isomorphic. Then if mu of X cyclotomic E1 is 0, then mu X cyclotomic of E2 is 0. So if the mu invariant of one of them vanishes, then the other vanishes as well. And they also gave an explicit formula for comparing the lambda invariance. All right. So this is the story. And we wanted to investigate this further. And of course, people have done that also, various others. And in fact, in particular, for those of you, I'm not going to get into the details of stating the Iwasawa main conjecture and so on, but the centerpiece in Iwasawa theory is a main conjecture. And then they also showed that if the main conjecture holds for one, then it also holds for the other. So there is a lot of information which is sort of caught when you look at the residual representations. And then similar results have been extended. For instance, you can look at, my work with Sudhanshu. Chandrakant also did this in the setting of HIDA families. And then later, Lim with Mengfei Lim, I proved this, and also with Filippo Nuccio, we carried this further to bigger extensions. But today, and then we wanted to investigate. So now the relevant conjecture we want to address is the following. Conjecture of A. This was a conjecture made along with Coates, John Coates, sometime in the early this century, around 2000. And the conjecture is that the fine Selmer group, Y cyclotomic of EP infinity, has mu invariant 0. In other words, this is the same as saying Y cyclotomic EP infinity is a finitely generated ZP module. The mu invariant is somehow one of the difficult invariants to work with in Iwasawa theory. And if it vanishes, then you're quite happy. So that's the reason you want to understand when the mu invariant vanishes and so on. And in fact, we showed, well, Greenberg already knew it, but I realized it, I gave a different proof and then realized after I had given the proof that Greenberg and Peranio, they were aware of this result, but my proof is kind of different. So this conjecture is also equivalent to saying, let me write, well, I'm over Q, say, in fact, we make this conjecture more generally for any base field. So this is also equivalent to Ks over K cyclotomic, the P torsion being 0. So you see, for the mu invariant of the fine Selmer group, you see that it is something that depends only on P, only on the residual representation. Okay, so this is the story so far for, and here this can have ordinary or supersingular reduction, both for ordinary and supersingular reduction. This was a conjecture. This conjecture is known in a large number of cases. And then in recent years, some of my students and postdocs and others have done arithmetic statistics in the sense of what is the proportion of primes for which you know this is true, and so on. And Greenberg and Watzel, their method of working with this is to introduce a residual Selmer group. Which I'm going to write Selmer of EP. In the sense you, instead of, remember there was this defining exact sequence for the Selmer group. right? Everywhere the Selmer group was defined by an exact sequence. So here, instead of taking the full divisible part, EP infinity, you just take EP here. So you can introduce the residual Selmer group, and they work with the residual Selmer group, and then they work with an imprimitive part, imprimitive Selmer group. That is, in the defining exact sequence, we had all the primes above S, but they throw away a few primes there. And then the idea is to say that this imprimitive Selmer group retains all the information that you wanted about the original Selmer group, namely the mu invariant and the lambda invariant is retained by this imprimitive Selmer group. And this imprimitive Selmer group turns out to depend only on the residual representation. So that's the method of Greenberg-Wurzel. And later with Meng-Fai-Lim, we work directly with the residual Selmer group. With EP, directly work with the residual representation and then use this part. Assume conjecture A. Assume conjecture A, which we know depends only on the residual representation, and then get a different proof, reproof, or get a totally different proof, in fact. Get a different proof of Greenberg-Wurzel in the cyclotomic setting. So this is what we did in the cyclotomic setting. And then in the anticyclotomic setting, now let's turn to the anticyclotomic setting. Here things are somewhat nicer because you know that the mu invariant of the anticyclotomic Selmer group is 0 in the ordinary case. But the proof of this is subtle. So again, this proof is due to a number of people: Bertolini, Darmon, Pollack, Weston. I have to mention a lot of names, Greenberg and all of them. But somehow this proof that the mu invariant is 0 needs a main conjecture. So it needs very heavy machinery. And then once you have that machinery, you know analogs of Greenberg-Wurzel's result. Okay, now this is the other subtlety here in what's called the definite case. So without again going into the details, let me mention in the anticyclotomic setting, there are two broad cases you have to consider. One is called the definite case. And let me define this in simple terms. There's a more, the reason that it's called the definite case comes from, comes from really Shimura variety theory and so on. So the definite case just means, for our purposes today, the definite case just means you have the conductor of the elliptic curve. And then it breaks naturally into n plus and n minus, two integers which are very important in the anticyclotomic setting. N plus is divisible by all primes split in k over q in the imaginary quadratic extension. And n minus is just divisible by the inert primes. So these are very important integers in the anticyclotomic setting. And then the definite case is the case when n minus has an odd number of divisors. And then the other case, this is a definite case, the indefinite case is the other case. And like I said, I tried to find, actually, I would be very interested if somebody in the audience knew a reference for where this was originally called the definite case and the indefinite case. I know that the terminology comes from, studying Shimura, associated Shimura varieties, and then the quaternion algebras being definite or indefinite. But this seems to be one of those things that experts know, but there's no history of why it came to be called the way it was called. So this indefinite case, well, both of these cases have been, and then you want to ask similar question, analogs of Greenberg-Wurzel. That is, if you have two elliptic curves which are residually isomorphic, then how do their mu invariants compare? How do their lambda invariants compare? So now with Filippo Nuccio, again, we had worked directly with the residual representation. The residual representation, we had proved analogs of Greenberg-Wurzel. For the signed Selmer groups. For signed Selmer groups in the anticyclotomic setting. Sorry, in the cyclotomic setting. And this again was different than the proofs which were in the literature, and we proved more than what was known in the literature. I will not get into this. But today, what I want to say is this theorem. This is due to a current PhD student of mine, Pam. Who proved the following. Okay, you need some technical hypothesis. Let me write down the hypothesis. Okay, there are 4 hypotheses. So good ordinary reduction. First is E has good ordinary reduction. At all primes above P. And then now, yeah, this is the contrast already in the anticyclotomic case. Remember, in the cyclotomic setting, we knew that the dual Selmer group was cotorsion. But here you have to make that assumption. It's no longer well, it is conjectured and it is known in a few cases, but not as sweeping as in the cyclotomic setting, where Mazur conjectured, and Mazur's conjecture is proved due by Kato in a large number of cases. So here it is substantially less. So we have to make that hypothesis. So X anticyclotomic EP infinity is lambda torsion. Then the Galois group is surjective. The Galois group of Q EP infinity over Q GL2ZP. So it's the full image. The image of Galois representation is the full image. And then this is again something that is similar to what happens in a super singular setting. In the cyclotomic case, you have this for free in a super singular setting, but here you need to make this hypothesis. So all of these are hypotheses. EFV of P is 0 for every prime V, which is bad and inert in K. And these are infinitely split. Such primes are infinitely split in the anticyclotomic extension. So this being infinitely split, so somehow makes the whole, gives a real twist in the anticyclotomic setting. So once you make this hypothesis, then the theorem is the following. Then the following conditions are equivalent. So remember, in the ordinary setting and in the cyclotomic case, this being lambda torsion was the same as the defining sequence being surjective. So that holds even here. If that is surjective, then it is cotorsion. So that's the analog even here. So let me write that map lambda anticyclotomic. This was the global to local map, right? We had the defining sequence for the Selmer group. So here. So you have something similar for anticyclotomic. So that's the lambda anticyclotomic, the global to local map in the defining sequence. So this is surjective. And the mu invariant of the fine Selmer group. Y anticyclotomic EP infinity. So this is, remember, this is the dual fine Selmer group, which is conjectured to be 0. So this is what we call conjecture A. So if lambda is surjective and this mu is 0, then you get that the dual fine Selmer group is cotorsion. Now I can define a residual fine Selmer group. So by which this is just the kernel of H1 Fs or Ks over K anticyclotomic EP going to all V in S H1 K anticyclotomic completed at all the primes above V, again the residual representation. If this, which is the definition of this, this has to be, now this is a module over the residual quotient Iwasawa algebra, FPG, which is isomorphic to FPT. If this is torsion as a lambda module, omega module, as a module over this. In other words, this is finite. Modules over these FP power series ring in one variable over FP, the torsion modules are just the finite modules. But now what is interesting is this already gives us the information that the Selmer group over the anticyclotomic extension has trivial mu invariant. And this was all this equivalences. Some parts of it was known, some parts were not known, but this last part was definitely not known. This last part is the exact analog of what we had in the cyclotomic setting, namely an analog of weak Leopold for the residual representation. So we have these 4 equivalent conditions, and then we also give analog of Greenberg-Wurzel's result. Result holds. This again was known due to polar question, but our methods are completely different. So the analog of Greenberg-Wurzel, this is all in the definite case, okay? Analog of Greenberg-Wurzel's result is known, holds. So if the mu invariant of, if you have 2 elliptic curves, which are residually isomorphic, and the mu invariant of one is 0, then the mu invariant of the other is 0, and also can compare the lambda invariance purely in terms of the residual representation. Comparison of lambda invariance when the residual representations are isomorphic purely in terms of residual invariance, purely in terms of quantities, I'll say quantities coming from the residual representation. This covers, our proof also covers a few more cases which were not covered earlier in Pollack Weston and so on. But in any case, these methods are completely different. And then somehow conjecture A, I find this quite striking because in the ordinary case, you always expect the fine Selmer group to have mu invariant 0, but you definitely don't expect the dual Selmer group to have mu invariant 0. But in this case, you're actually, of course, if the fine Selmer group has mu invariant 0, sorry, if the dual Selmer group has mu invariant 0, then the fine Selmer group has to have mu invariant 0 because it's a quotient. So conjecture A is true if the mu invariant of the Selmer group is 0. But it's often difficult to say anything about the mu invariant of the Selmer group once you know conjecture A. So this seems to be saying that something interesting is happening in the anticyclotomic case, and we are currently investigating more. And the indefinite case turns out to be more delicate. And I haven't wrapped my head, we haven't wrapped our heads around that fully. Indefinite case seems considerably more delicate. To attack via this approach. So what we are trying to do, and in this case, the indefinite case, it seems difficult to work with this, the usual Selmer group on the nose because you don't have this exactness. The defining sequence is not exact. So that makes it slightly difficult to work with. But in this case, there is another Selmer group constructed by Bertolini, Darmo, and Prasanna. So let me call that X anticyclotomic BDP, EP infinity over K anticyclotomic. So this is the dual Selmer group defined as per Bertolini, Darmo, Prasanna, where the local conditions are now quite different. And I still have not understood what is the reason for this. Well, and then of course, working in that setting is also, you have much more information. You have lots of results due to Bertolini, Darmo, Prasanna. For instance, you have Euler systems, you have the Hegna points. So you can do much more interesting Iwasawa theory there and probably get more evidence as to what a mod P Iwasawa theory should look like. What can you expect? So that's the project we are currently thinking about, we are working on. And our goal is to sort of reprove or recover all the results that we know in the cyclotomic case to find their analogs for these different Selmer groups in the anticyclotomic case. So let me stop here. And our idea is to first understand Greenberg-Wurzel for the Bertolini, Darmo, Prasanna anticyclotomic Selmer group, because that seems to be slightly easier to work with than the classical Selmer group. And then hopefully compare the classical Selmer group with the Bertolini, Darmo, Prasanna Selmer group. And then recover what can one say about the comparison of mu invariance and the comparison of lambda invariance. Again, working directly with, instead of working with EP infinity, working directly with EP. And so there are also numerical examples where what we have done can be illustrated quite nicely. And because there are Hegna points in this case and Euler systems, so this offers a very interesting arena to investigate Iwasawa theory in this, and also the mod P Iwasawa theory. With Chan Ho Kim, by the way, Chan Ho Kim has partially done this, but we want to approach it slightly differently, working directly with the residual Selmer group. So that's sort of what I wanted to say. And thank you very much for your attention.
Are there any questions?